Hello, I'm Quinn Turner, and I will be presenting my final project for numerical computation, the interpolation of regular, conventional retail gas prices in the United States. Um, so my main research questions that I was aiming to answer were, can numerical interpolation methods accurately model historical U.S. gas prices? And some secondary questions were, which techniques yield the lowest error, and what is the sensitivity of these techniques to the features? So, my motivation for exploring this was to identify the impact of policies and geopolitical events on gasoline prices. Like, for example, if the interpolation turns out not to be as accurate as predicted, especially in spots where there's political turmoil, that would point to the importance of geopolitical events. And I also wanted to explore more data-driven numerical methods. So previous literature on this topic includes using the features gross domestic product, consumer price index, unemployment rate, and the federal funds rate, using models like exponential smoothing, Holt-Winters, ARIMA, which is autoregressive integrated moving average, as well as support vector machines, neural networks. And it was found that SVMs actually outperform ARIMA and neural networks, but that was a paper that was published a while ago. And more recently, long short-term memory models with gray modeling for multi-step forecasting has surpassed that. But there's very few studies overall in numerical interpolation methods used on gas data. So for my data, I used just gas prices, crude oil prices, employment rates, CPI, and crude oil production. So one of the numerical methods I used was Lagrange interpolation, where you fit a degree n polynomial through n plus 1 points, where pxi equals yi. And one issue with this method is that it is prone to Rugna's phenomenon, which means that it basically oscillates at the end of the interpolated interval. I also used Newton's divided differences, which actually builds the same polynomial to Lagrange polynomial, but it's easier to update with new points. I used cubic spline interpolation, which uses basically piecewise cubic polynomials and ensures the second derivative of the splines basically are continuous. I also used a numerical method that was not covered in class but is covered in the textbook, Hermit interpolation, which instead of just matching xi to yi, it also matches the derivative of the interpolating function to the derivative of the output. And in this case, I used the divided differences method, so very similar to Newton's method, but instead of just fitting it to h of xi equals yi, I'm also fitting it to the derivative, which means that you're fitting a polynomial of degree less than 2n minus 1. And I also experimented with Chebyshev nodes to minimize Runge's phenomenon. So I really was trying to find a optimal model to predict gas prices based off of one of the explanatory variables. So in order to do that, I had to analyze all of the combinations of different options I had. So here are the things that I chose. So I had different interpolation methods: Lagrange/Newton, cubic spline, and Hermite. I had to choose the number of interpolating points. So I ended up experimenting up to 13, but I found that points like 11, 9, 7, and 5 points generally gave me the best, so I created a table using those. Point spread. So I used like within the interpolating interval, how those number of interpolating points are spread out among it. I used three different techniques: random, equal spacing, and Chebyshev. And then I evaluated across three different errors. So I created a table with all of these interactions, and then I built the following, which is the mean of the different types of errors across these numerical methods. So Lagrange and Newton interpolating polynomial, the mean error was extremely high. But the same goes for cubic spline and Hermite. The mean absolute error isn't as much, but it's not very good. So then I looked at the median error. And for Lagrange interpolation, it's still very high for mean squared error. But for cubic spline and Hermite, it dropped very significantly, which means that this is a very viable prospect. So then I also looked at the different ways of spreading points. And so these are the medians again. The means were very high. Same thing. These distributions of errors seem to be very right skewed. So I use the medians to evaluate them. So Chebyshev is significantly better by magnitudes compared to equally and random. And then using Chebyshev and mean squared error, I created this table, which shows the feature on the left that I selected and the model going from left to right. And in each tuple I have there, the left is how many points are used for the interpolation, and the right is the mean squared error. And these are the optimal for each. So this is an example of one of the graphs of an optimal model. Or the optimal model given you're predicting gas price based on crude price. So in this case, the best would be using 7 interpolating points, Chebyshev, using Hermite interpolation, which you can see is the green dotted line. And the black dots here represent the other data points that aren't being used in the interpolation to make sure that the model is generalizing correctly, because you don't want to over underfit based on like a bad choice of initial points, and you want to make sure that it at least visually lines up with the other points. So my key findings after doing these analyses were that Hermite was by far the best method by median error in predicting gas prices across all features. Cubic splines came in second, and Lagrange or Newton divided differences came in last place. And as far as node distribution goes, Chebyshev also has the best median. If you're looking for the best mean, equal spacing is the best. But Chebyshev, I found, only really fails in a couple circumstances where the error is terrible. So if you needed an accurate model for all these cases, I would just recommend using equal spacing for those couple cases where Chebyshev fails. And Chebyshev probably fails because of the coarse sampling and the non-continuous nature of the functions, because you can't get the perfect Chebyshev sampling across the interval, because it's not guaranteed that that point will have an existing value there. So that's one of the problems, which can be fixed with a different sampling method. Then I also figured out that crude price and CPI were the most explanatory, followed by production, and unemployment at the least. So I also looked into doing linear regression. So here I'm looking at the VIF to look for multicollinearity, and CPI is the highest, which suggests it has a linear relationship with another one of the variables. So I did this first model. The R squared is extremely high, MSE is very low, which probably means it's overfitting. So I removed CPI, and the R squared and the error rates, R squared went down, error rates went up a little bit, but the VIS went down by a lot. So that probably means that it's generalizing slightly better, and the regression coefficients told me that on average, as crude oil price goes up by $1, gas prices go up by $1.26. 1% unemployment leads to 1 less cent in gas prices, which was actually surprising. Thought it'd be more significant than that. And the gas production had very little effect on the gas prices. And the unemployment coefficient of p-value was greater than 0.05. Thus, it's not very significant anyways. And these observations align with my observations from the the application of the numerical methods. The implications of this are that the method and node selection is very critical if you want high interpolation accuracy. And some of the limitations that I mentioned earlier were coarseness of the data, and that I am also assuming that the underlying distribution of gas prices would be able to be modeled by a smooth polynomial function, which is not always true. And in the future, I'd like to see maybe more dynamic node placement techniques to overcome the like the coarse sampling. I would also like to see more multivariate interpolation because I only did univariate. And hybrid methods would be really interesting, mixing interpolation with different machine learning algorithms like long short-term memory models. And then I also think that including more features and then using principal component analysis or possibly like lasso would also improve the models in general and would really help with the knowledge gain. So these are my sources, and thank you very much.